In this video, we will discuss AI system design. So we take one example of supply chain risk intelligence platform, and we will learn that how we can design the system of that application. Okay. And the application is supply chain risk intelligence platform. So let's first understand that what exactly this platform or this application is all about. So we know that supply chain is extremely complex system, right? So in a whole system, we have multiple suppliers, multiple manufacturers, distributors, right? There are a lot of documents, contracts. So it's a very complex system of any supply chain project, right? And when we have lot of different parties like manufacturer, distributors, right? We have documents, contracts. Now it is extremely difficult to answer such questions like which products depend on this supplier, or what happens if supplier A goes bankrupt, or which factories are indirectly affected by some port closure. So these are the questions that are extremely difficult for any supply chain platform to get the answers, right? And the reason is because of siloed data. Okay, because the data is siloed. So what is the meaning of siloed data? The siloed data means the data in different systems or different applications or different departments that are very difficult to share. Or in other words, there are multiple systems has their own data, and the data is not easy to share among multiple systems. So what happened when the data is not easily shared among multiple systems? In that scenario, it's very difficult to extract the information, right? So first you have to go to one system, get the information, then we have to again hop to the second system to get the information, right? So it is extremely difficult to get one information from multiple different systems. Then the second problem is the hidden dependencies, right? So critical dependencies across multi-tier suppliers and locations are unknown until the disruption happens. Then the reactive risk management, unstructured data, okay, no unified view for decisions. So these are the problems that we are solving by using this application, which is the supply chain risk intelligence platform. So what is the solution? The solution is an AI powered supply chain risk intelligence. Okay. So our platform connects data, intelligence, and AI to give you complete visibility. Okay. So here in this application or here in this platform, we have the unified knowledge graph. So we'll discuss that how we implement knowledge graph in this system. We have AI powered insights. We have proactive risk detection. We have intelligent document understanding. That means we extract documents from multiple sources, right? So now we don't have the data silo problem over here where we have to hop into multiple systems to get the data, because we have a vector or a document understanding system. So we collect data from different systems and store it into a vector database. And we will also discuss that how we can do that while we design the system of this application. Okay. And then finally, actionable insights, actionable intelligence, right? So risk scores, impact analysis, alerts. If so, these are the things that we will implement in our platform. So this is a supply chain risk intelligence platform tool. And our job is to design the system of this application or this platform. Okay. All right. Okay. So, so the business problem, we have understood that what exactly the problem of the supply chain system and how we can solve that using AI, using knowledge graph, and using vector database, right? Or using the retrieval augmented generation or RAG. Okay, so the hidden risk is that modern supply chains are complex webs. As I said before, modern supply chains are very, very complex, right? Traditional systems miss hidden dependencies, right? The business impact, a single bankrupt supplier or a geopolitical event can halt production, costing millions. right? The missing link, we need relationship intelligence connecting the dots across the entire network. So when we start connecting the dots, then we get a bigger picture. And when we have a bigger picture, then we can give the proper answer of that. So that is how we reduce the cost, we reduce the loss of any supply chain network. Okay. So in this application, we have multiple stages. The first stage is the upload, right? Obviously, in order to give answer, in order to extract the no the insights, we need data, right? So we need to upload the company data. Okay. Then we have to do the analysis, right? So system extract the data and put it into the graph database and the vector database. Then the third important component in our application is going to be a monitor, right? So the background engine that continuously monitor and give us the prediction of what could be happen next. And then finally the query. So we will have a chatbot where the users can ask questions. And because we have data from different sources, so we can extract information from the data, right? So the primary users, supply chain managers will use our application, risk analyst, okay, procurement. So these are our primary users. Functional requirements. So document parsing, global news monitoring, entity extractions, AI chat interactions. So these are the functional requirements. Now note that when we start designing any application, it is important to first analyze the functional requirements and the non-functional requirements. Okay. Functional requirement means what the system should do, or in other words, we are designing the system, right? And the system should be designed in such a way that it should handle, or it should do some kind of an operation, right? So what type of operation or what the system should do, that comes under the functional requirements. So in this case, the functional requirement says that document parsing, global news monitoring, entity extractions, AI chat interaction. So these are the functional requirements. The non-functional requirements, that means the technical point of view of the system. So the system should be highly available. Okay. Sub-second search latency, that means whenever any user search something, we have to, or the system should return the result in very low in very fast way. All right. So that is called the sub-second search latency. Then highly secure multi-tenancy. So what is the meaning of highly secure multi-tenancy? The reason is because this is a platform, right? This is a tool that we will give to the clients, right? So what are the clients? Clients are the supply chain managers, the risk analysts who will use the tool. And we could have multiple clients, right? So there is one company, company A, company B, company C, right? So there are multiple clients, and multiple clients, they share the data and they trust a platform. Okay. Trust is very important when they use this kind of a tool, because they share their internal data to the platform, to the tool. Okay. So we have to make sure that the data cannot be compromised, right? So when one client upload the data, it should be in the sandbox of that particular client. It cannot be moved to another client sandbox, right? That we have to make sure, and that is how we have to design the system, right? So this is called the this all comes under the non-functional requirements, right? Okay. Now we have understood that what are the components of our application, and what is the functional requirement, and what is a non-functional requirement. Okay, now let's discuss the high level system architecture. We will break down each and every component, but it is important that we first, in our brain, when we design the system, right, it is very important that we put some picture, a high level picture on our inside our brain, so that we can design the system properly. And this is the step. Okay. So the first is the data ingestion, right? So we have data in documents, in CSV files, in Excel files, in PDF files, so in APIs, right? So we have data in different formats. And then there is one pipeline. So the pipeline first extract or get the data, extract the information, right? And then store it into the knowledge graph and the vector database, right? Now, if the data is structured data, then we store it into the knowledge graph. If the data is unstructured data, right, for example, PDF, right, so that we will store into the vector database. And then finally, you have the intelligence layer. And in the intelligence layer, we have the the chatbot where the user asks question, and we extract the information from both the knowledge graph and the vector database, right? And also we have one more component, which is the background risk engine, and that engine will continuously monitor the risk that is happening in the whole supply chain network, and it immediately warn us with some signals. So how it all connects? So built on event-driven microservices. So we will design a microservice architecture for this system. We for the graph stores, for the structured relationship, we will use the graph database. For the vector DB stores, it's mostly the document, right? For the PDF, so that we store into the vector database. For the output, serves actionable insights via the chat and the dashboard. So this is the very high level idea or the architecture of the application. Okay. All right. Now this is the knowledge graph. Now how we design the knowledge graph, this is very important because in our whole application, if you carefully monitor, we have multiple components, right? One component is to design the pipeline. Okay. And the pipeline is to get the data, extract the content and store it into the knowledge graph and the vector database. The second component is the design the dual brain, right? To design the knowledge graph, design the vector database. And the third layer is the intelligence layer, where we design the chatbot, we design the background risk engine. Okay. So first let's discuss that how we can design the knowledge graph. Okay. So for that, I print this Blackboard. Okay. And now let's discuss the graph rag, or in other words, knowledge graph. Okay. All right. So what is a knowledge graph? A knowledge graph is a structured representation of the real world entities and the relationship between them. So what I said that a knowledge graph is a structured representation of real world entities and the relationship. That is knowledge graph. And how we can design a knowledge graph? So to design a knowledge graph, there are multiple steps. There is no straightforward way to design the knowledge graph. In other words, we have the document, right? And let's say that, okay, we have the document, let's put it into a graph database. Let's say that we use Neo4j. So we have the document, use an LLM or any LLM model and store it into the Neo4j. That is not happen in real production environment. There are multiple steps involved when we design a knowledge graph in a production environment. Okay, so let's first discuss those steps. Okay, so the first step to design a knowledge graph is this. So first step is define the domain and use cases. So let me write define the domain and use cases. This is the first step. So the first step says that what questions must the graph answer? This is very important, and this is the step number one when we design a knowledge graph, right? So what question must the graph answer? So in beginning of the video, I said that a user can ask multiple questions, right? A question like which product depends on a single supplier? What happens if supplier A goes bankrupt, or which contracts are about to expire? So these all are the questions, right? And if we design a knowledge graph, the graph must answer this type of questions, right? And these are real world questions, right? When I say that which contracts are about to expire, that means I'm talking about contracts. I'm talking about contracts between multiple suppliers, right? A contract between one supplier and one manufacturer, right? So these are the real world entities I'm talking about. So the first step is to define the domain and use cases. In other words, what the graph must answer. And This also called competency questions or CQ. Okay. This is also called competency questions or CQ. So this is a step number one. So step number one means we design the competency question. That means what the graph must answer. Then step number two. In step number two, we design the ontology. Okay. So we design ontology. Now, what is ontology? Now, if you're familiar with RDBMS, you may design schema, right? And in knowledge graph, you can say that this is very similar. Although ontology and schema, those are completely different thing, but you can imagine as of now that ontology in knowledge graph point of view is similar to schema in RDBMS point of view. Okay. So in ontology design, what we do, we define the entity, we define the relationship, and also we define the properties. These things we define in the ontology. So the first step is to uh, create the competency questions, and the second is to from that competency questions we design the ontology, right? And how we can design the ontology? To design the ontology, we also use LLM, right? So how we can use the LLM? So let's say that we have the competency questions ready, and let's imagine that we have total 100 competency questions. So we design the 100 competency questions and we pass the competency question to an LLM and ask the LLM to create or design the ontology, right? So the LLM design the ontology, and the next step is we verify or we review the ontology. We should not blindly trust the LLM to create the whole ontology. This is a very important step. So in the ontology design step, we use both the LLM as well as the human review to refine or create a proper ontology, right? And ontology means we define the entity, we define the relationship, and we define the properties. Okay. So this is the step two. And one more thing, if you are not familiar with what is entity, relationship, properties, then probably you have to do a research on what exactly these things in a graph database point of view. You just search in ChatGPT or in any AI tool and you get the idea of what exactly these things. Okay. All right. Then this is the step two. The step three. The step three. Step three is a data ingestion. Okay. So the step three is data ingestion, right? Now, if you see our slide, in our slide, what we have the data, right? And then we have a data, we have a pipeline, right? And the pipeline is then store the data into the knowledge graph. So that is the step of data ingestion. So we have the data, we ingest the data into the knowledge graph. Okay. So this is a step that we are talking about. Okay. So data ingestion step. In the data ingestion step, what we have data, right? So we have data, and data may be in PDF, data may be in CSV files, right? Data may be in Excel file, like that. But the data should be structured data. That means there must be some relationship present in the data. If there is no relationship, the data is completely unstructured, then what we will do, we move to the second pipeline, which is the vector DB. So we store the data into the vector DB, right? If you look at our slides, this is our second pipeline, if the data is unstructured. But if some relationship is present, then we go to the first pipeline. Okay. So this is our data. Focus on this part. So this is our data. And for now, this is a unstructured data. So what we'll do now, the next step is that we extract the content from the data, right? So because our data is in CSV file, in some APIs, in Excel files, in PDF files. So we do the extraction. right? So we do the extraction. Also, we perform some filtering. So these are the steps that we need to perform. And after that, we now have some uh, polished data, or let's call it clean data. And we pass the clean data to the LLM. So we will use a large language model. Now, here is a question. What type of model should we use? Should we use any open source model? Should we use any closed source model? That questions depend upon the organization to organization. That means cost, security, budget, a lot of factors are involved when we choose between a open source model or a closed source model. Okay. But as of now, let's say that we choose a proprietary or a closed source model. Maybe GPT-5 we choose for this LLM, right? So now we have a clean data and we pass the clean data to the LLM. And what we expect from the LLM to do, we expect the LLM to return us a structured JSON. Now note that we need to store the data into a knowledge graph, right? But we cannot directly store any kind of an data to the knowledge graph. That is why we design the ontology, right? Because in the ontology, what we did, we create the entity, the relationship, and the properties. And in the data, we first check that does the entities present in the data or not? Does the relationship present or not? Does the property is present or not? We cannot directly or randomly put any entities, any relationship, anything into the knowledge graph. That is not possible, right? So how the LLM will know, or how the LLM generate a proper JSON that we can add into the knowledge graph. So what thing we need to pass to the LLM as a context? So we need to pass the ontology design that we created in step 2, right? We pass the ontology design as a context to the LLM, right? So what we have the clean data first, we have the ontology design second. We pass both to the LLM, and finally the LLM generate a structured JSON. Okay, so this is the whole flow, right? So if you look at our diagram, so as I said before, that this is a pipeline, right? And there are multiple things happen in this pipeline. And we are now talking about this pipeline, right? So the whole thing, okay, is under this pipeline. Clear? Okay. So now we have the uh, structured JSON. Now that is not the end. Once we have the structured JSON, the next step is to pass that structured JSON to a validation layer. So we pass it to a validation layer. So what we do in the validation layer? In the validation layer, we do multiple things. So we perform schema validation. Okay. So we perform schema validation. In the schema validation, what we do? So did the LLM follow the ontology? So did the LLM follow the ontology? This is come under the schema validation. Then confidence threshold. So confidence threshold. So confidence threshold means how sure the LLM is. This comes under the confidence threshold. The third is business rule validation. Okay, business rule validation. So domain specific sanity check we perform in the business rule validation. And there are multiple other things that we do in the validation layer. Now, after the validation layer, the next step or the next layer is the entity resolution layer. So the next thing is the entity resolution layer. So what we do in the entity resolution layer, in this layer, we check if any entity already exists or not. So what does it mean? Any entity already present or not. So let's say that after extraction, we have one name. The name, let's say John Smith. This is one name. And again, we have one name, J. Smith. So we have to check, does this two person same or not? If not, then we have to create two nodes, right? If it is same, then there is no need to create two nodes. So the next step is to write in Neo4j. Okay, Neo4j is a graph database, right? And how we can write it into the Neo4j? Simple, we create the cipher query so that we can write it into the Neo4j. So this is the pipeline for data ingestion into the knowledge graph. Okay, so this is our first pipeline. So we have the data ingestion layer, then we have this pipeline. This pipeline is nothing but this thing, whatever we have discussed over here, right? And then after we store it into the knowledge graph. Okay, all right. Now we have one more thing. The thing is the vector DB. So how we store the content into the vector database. Okay. So for that, again, we will discuss the ingestion pipeline for vector database, or in other words, the RAG pipeline. So now let's discuss the RAG pipeline. Okay. So first we have the documents, right? And for the RAG pipeline, the data should be unstructured. So first we have the document. So the document is maybe PDF, some doc files. It could be CSV, but mostly PDF and the docs file. Then the second step is the text extraction. So we have to extract the text, right? So the text is present in the PDF. There are headers, there are spacing, there are footer, a lot of extra things there in the PDF file. So we have to all remove this thing before we store it into the vector database. So this step is a text extraction and text cleaning. So these are the two very important steps for a data ingestion pipeline for the to store the data into the vector database. So text cleaning. First is the text extraction and the second one is the text cleaning. Then document metadata extraction. So the next step is the document metadata extraction. So what we do in the document metadata extraction, here we extract the metadata. That means what is the document type, the access level, the timestamp, the year. These are the document metadata. And there are a lot of things that we can explain or we can discuss in the document metadata extraction. But as of now, just note that document metadata extraction means the metadata of the document. So you have to also extract that thing. Then the second thing is the chunking, is to create the chunking. And to create the chunking, we will use the parent child chunking. Very important. There are many different chunking strategies. We have the fixed size chunking, we have semantic chunking, we have parent child chunking. And in this scenario, we will use the parent child chunking. And the reason is because parent child chunking is widely used in enterprise application. Okay. So once we have extracted the metadata from the document, the next step is the parent chunking. Okay. So we will do the parent chunking. In the parent chunking, we can also extract the metadata of the parent. Okay. So the parent metadata extraction. So you can imagine that we have a PDF file, right? From the PDF file, we extract the text, we clean the text, and from that, the big large text, we extract the metadata and we call it the document metadata extraction. And here we split it into some parent chunks. Okay. Maybe these chunks are 800 to 1000 tokens. Currently, this is a very big chunk. We split it into multiple chunks and we call it parent chunks. And the parent chunks are mostly 800 to 1000 tokens chunk. And from individual chunks, we can also extract the metadata. Okay. And this is called the parent metadata extraction. Okay. So if I give you one example of the parent metadata extraction, maybe so one chunk may contains business unit, project, quarter. So those kind of an information we store as a metadata. Okay. Okay. All right. So the next step is the child chunking. So the next step is child chunking. So in the child chunking, so understand that we have the parent chunk. And what is the size of the parent chunk? The size of the parent chunk is almost 800 to 1000 tokens, right? But that is a lot of tokens. The chunk is still very large. So what we'll do, we further split it into small chunks, maybe 100 tokens. And that is called child chunks. So one parent chunk is further split into small chunks, and that is called child chunk. And one more thing I forgot over here. When we create the parent chunk, we also store the parent chunk into a into a storage layer, maybe MongoDB over here. So we store one parent chunk into the MongoDB, and what we get the ID, and the ID is a unique per parent. Okay, and then we further split the parent chunk into smaller child chunk. Now here, what we'll do after the child chunking, we do the metadata inheritance in the child chunk. Very important. So here we do the metadata inheritance in child chunk. So we include the document metadata, right? Then parent metadata, then child chunk. Okay. So in the child chunk, we do the metadata inheritance. And in the metadata inheritance, we add the document metadata, parent metadata, and the child chunk. And after that, what we'll do, we do the embedding. Okay. So we do the embedding and this is very important. We never do the embedding of parent chunk. We always do the embedding of child chunk. Okay, so always remember, we always do the embedding of child chunk. Okay, and after that, what we will do? We will do BM25 indexing. Okay, BM25 indexing. So maybe this is for that we can use some other services. Let's say that we can use Elastic Search service for the BM25. Okay, so basically we do the indexing on the child chunk text, not the embedding. Okay, very important. We do the indexing on child chunk text. Okay, after that, once we have the embedding ready and after we do the indexing, the final step is to store it into the vector database. Okay, so this is the whole flow for the RAG pipeline. So we basically, what we did, we basically extract or go deep into the whole pipeline. So we have the data ingestion and we have the dual brain where we store the data into the knowledge graph and the vector database. And what happened behind the scene that we have discussed over here. One is the knowledge graph data ingestion and the second one is the RAG pipeline. Okay, so I hope that is clear to you. Okay, so the next is the knowledge graph, design the ontology. We have already discussed this thing. So why a graph? Supply chains are literally graphs. Relationship matters as much as the entities themselves. The entity resolution, the system must deduplicate. Example, merging the Apple Inc. and Apple into one node that we have already discussed, right? And provenance, early node contains metadata tracing exactly back to its source document for auditing. So the next is the graph construction, the guardrail sandwich. So the LLM purpose is to unstructure the data goes in, the LLM extract the entities into the JSON format. Then the deterministic code strictly validate the JSON against the business rules and our ontology. And the third one is a safely writes to Neo4j via the idempotent updates. This is basically what we have discussed this thing. Okay. Okay. So the extraction, filtering, clean the data, structured JSON, validation layer, entity resolution, right to Neo4j. So this is basically the whole thing. Then the next thing is the graph RAG. So smarter AI chatbots. So the traditional RAG is only vector only. For a graph RAG, we have the hybrid approach. That means we have the graph traversal, we have the vector search, right? The context is fragmented for the traditional RAG, but for a graph RAG, it is full relationship context. The hallucination risk for the traditional RAG is medium, but for the graph RAG system, this is very low. Semantic parsing. So the LLM translates a user query into the DSL. We will discuss what is exactly the DSL is in some time. Then the entity grounding. So matching the user's word apple to the exact database. Then the grounded AI, the chatbot aggregates the graph context and generates the answer only from the written data. Okay, now before discussing the further, what I want to first explain that how the retrieval should look like, okay, or how we can design the retrieval flow. So, so for that, let's discuss the retrieval flow. So the retrieval flow for knowledge graph. Okay, so in the retrieval flow, as I said before, that we have a desktop application or or a browser application where the user can ask questions, right? So there is a chatbot application, right? In the chatbot application, what we receive the user query, right? We receive the user query. So once we receive the user query and our data is present into the knowledge graph. For now, let's focus on the knowledge graph part. So our data is present into the knowledge graph. Once we have the user query, our job is to extract the content from the knowledge graph, right? That is our goal. So we have the user query. The next step is the LLM semantic parser layer. So what is this LLM semantic parser layer? In the LLM semantic parser layer, we do couple of things. The first thing we do over here is intent extraction. Okay. Intent extraction from the user query. So what the user or what is the intent of the query of the user? That is a simplest thing of the intent extraction meaning. Then entity recognition. So the entity recognition. That means in our knowledge graph, we have multiple entities, right? How many entities we have to extract based on the user query? That is the entity recognition meanings. Then metrics extraction, time context extraction. There are multiple things that they are in the LLM semantic parser step. And during the LLM semantic parser step, we also pass the ontology as a context, right? And in this layer, we have a combined layer as well, and that is called the graph query DSL. So after this two layer, what we'll get? We get a DSL. Okay, DSL stands for domain specific language, right? So this is basically the structured meaning of the user query in JSON format. That is the simplest definition of the result that we get after this two step. Okay, so after this two step, what we get the um, structured meaning of the user query in JSON format. Okay, and for that we have to use one LLM. Otherwise, it is very difficult to get the DSL. Okay, so this is a step. The next step, okay, the next step is the ontology validation. So the next step is the ontology validation. So in the ontology validation, what we do, we validate the entities, we validate the relationship, we validate the properties. So that thing we will do in the ontology validation step. The next step is the graph query planner stage. So the next step is the graph query planner. So in the graph query planner, what we'll do here, we determine the traversal strategy. So we determine the traversal strategy. We determine the aggregation strategy. So we determine the aggregation strategy. That thing we do in the graph query planner step. And after that, after this step, what we do, we do the query AST. So what is the query AST? AST stands for the internal structure representation of the query. Okay, so AST stands for the internal structure representation of the query. Now note that we have multiple steps, right? And you may say that why do we need to perform so many steps? We have the user query, directly send the user query to the LLM, and the LLM then generate the Cypher query and we execute the Cypher query. Why do we need to perform so many steps? The reason is because hallucination. What if, because this application is used by the large, large clients, right? We serve this the application to large clients who pays us a lot of money. So for that, we cannot build a system which hallucinate, right? So we need a proper step. We need proper guardrails in each and every step so that we get a proper response. Because one hallucinated response could create a major loss for our client. And that we don't want. So that is why we have multiple steps. So first we have the user query. Then we pass it to some layers. The first layer is the LLM semantic parser and the graph query DSL. Along with that, we pass the ontology as a context to the LLM, and the LLM generate a structured meaning in the JSON format. Then we pass it to the ontology validator layer, then graph query planner, then the query AST, where we get the internal structure representation of the query. And the hardest part of this pipeline is to generate a AST. From the user query to create a valid AST is the hardest and most difficult part of this whole pipeline. Okay. And what is the next step? The next step is the graph compiler. So once we have the AST ready, we pass it to the graph compiler. Graph compiler. Okay. The graph compiler will compile the AST to Cypher query. And after that, once we have the Cypher query ready, we do the Neo4j execution, right? And then finally we have the result. Now the result means the context, right? The context from the knowledge graph that we extract. Now we have the context. Now we have the user query, and then we pass both to the LLM for the proper response. That is the full flow of the retrieval process for knowledge graph. Clear? Okay, perfect. Now we have one more retrieval pipeline for vector database, right? So now let's discuss the retrieval pipeline for, so the retrieval pipeline for the vector database or the RAG system. So again, we have the user query, then we pass it to the query understanding layer. So we call it the query understanding layer. What we'll do in the query understanding layer, we do the metadata extraction of the query. Okay, maybe the client, region, year, project. Based on the query, we extract those metadata. So in other words, here what we do, we extract the metadata of the user query. And after that, after this step, we pass it to the metadata filtering from the child chunks. Remember, we stored the metadata in the child chunks, right? And after the user query, when we extract the metadata, we do the metadata filtering from child chunks. And after that, what we get some relevant child chunks. So we get some relevant child chunks. So once we have some relevant child chunks, what we'll do, we first do BM25 search. Remember, we use a service called Elasticsearch where we store the child chunk text. So once we have the relevant child chunks, we first go to the BM25 search. Along, we do the vector search. That means the semantic search. Okay, and after this two step, what we get some result, right? So we combine these two result and we pass the result to a re-ranker. Now I am not going to go deep into each and every step. I assume that you already familiar of these steps. My idea is to how we combine all the dots together to build a system. That exactly what I want to show you in this video. So we pass it to a re-ranker. After the re-ranker, what we get the top relevant child chunks. Okay, so top relevant child chunks, right? And after that, from the child chunks, and note that for each and every child chunks, what we store the parent chunk ID as well. Remember, the parent chunk is stored into the MongoDB, and we have the ID. And we stored that as a metadata to the child chunk. Now, once we have the relevant child chunks, what we can do, we can take or we can extract the parent chunk as well, right? Because we have the ID. So we query to the MongoDB, we take the parent chunk. So here what we'll do, we do the parent child lookup, parent child lookup. Okay. And then the retrieve parent chunk. So once we retrieve the parent chunk, we can also do some deduplication step over here. If two parent chunks comes, then what we do, we discard one and we select the one. Okay, so we do the deduplication one. So after that, we have the context ready, and then we pass a context along with the user query to the LLM, and finally, what we get the result. So this is a flow for the retrieval process for the RAG system. Now, so far, if we summarize this thing, then we have one service. So let's say this is one service for knowledge graph, data ingestion. Okay. Then one service for knowledge graph retrieval. Okay. One service is for the RAG or vector database ingestion. This is also ingestion, right? One service for RAG ingestion and one service is for RAG retrieval. Now, if we want to design a system which can handle a lot of traffic, a lot of load, then how we can do that? Okay. So let's say that we have data. So data from different clients. So let's say that we have a client A, then we have a client B, then we have a client C. So like that, we could have multiple clients, and multiple clients can upload multiple documents, right? So for that, we need a queuing system over here, or a queue system, which can handle that load, right? So for that, we use Kafka. So the documents, PDF, CSV, everything is come under the Kafka. And here is one important thing. We should not pass the files, documents into the Kafka. The reason is because the files could be very large. So first, because the clients will use one application. So first we have to store that into some storage layer, maybe S3. After that, we get the URL, and then we use some service, Kafka publisher service, and that service publish the event to the Kafka. Okay. Now, once the event is published to the Kafka, now we have multiple services present, right? So one service is for the service for kg ingestion, right? So this service take the event. One service is for the RAG ingestion. So when the event comes for the RAG ingestion, it takes the event from the queue and do the processing and store it into the vector database. Now the question is that how we can scale this thing. Let's say the load is very high, then how we can do that? As I said before, that these are services. Now, if we use a Kubernetes cluster over here, then what we can do? We can spin up multiple pods. So let's say that we spin up total 3 pods. So 3 pods for this, 3 pods for this. Also, what we can do? We can introduce HPA, horizontal pod autoscaling. So if the load is very high for some particular time, the HPA automatically spin up those services. And note that these services are completely independent with each other. The RAG service does not dependent on the kg service. The kg ingestion service does not depend upon the RAG ingestion service. So these are completely independent services. So this is very easy to scale up, right? So if we introduce the HPA or horizontal pod autoscaler, then during the peak load, we can increase the services. That is how we can handle that load. Okay. And here we can also use something called LLM caching. So we can add a Redis over here. Now, when the Redis will helpful. So let's say that any user ask a query, and first the query comes to one of the service. Okay. The service check that is that question present into the Redis cache or not. If not, then what happened? The service understand the user query. Based on that, it call any of the services. So we have 2 more service, right? So we have service for RAG retrieval. Then we have service for the kg retrieval, right? So it called the RAG retrieval or the kg retrieval. It extract the content. It extract the result, right? And it store the result into the Redis. That is how when the next time any user asks similar question, what we do, we first do the semantic search into the Redis. That is a similar question already present into the Redis or not. If it is present, we simply return that to the user. We don't need to call the service because the service operation is expensive, right? We have the LLM calls over there. and there are a lot of steps are involved over here. So this is how we can save the resources as well as the LLM calls by introducing the Redis or LLM caching over here. Okay, so this is the high level idea or the architecture of how we can design this thing. The main thing is that we have to design a KG ingestion and the KG retrieval, and we can treat these two as a separate services. We have the RAG ingestion and the RAG retrieval, and we and these two are treated as a separate services. We can spin up multiple services if we use Kubernetes. So we can spin up multiple pods, right? If we use the HPA, then if the load increases, then we can increase or decrease the pod count. So this is how we can handle that load. Again, we introduce a LLM caching layer over here. So first, when the request comes in, the request checks in the Redis. If the question is present, then it simply return back to the user. Okay, so this thing is defined over here. So why asynchronous? So processes heavy AI tasks or on large documents synchronously would crash the UI. Decouple ensures speed. Then Kafka partitioning enables parallel ingestion of millions of data points simultaneously. Resilience: if a worker fails, it retries. If it fails completely, it routes the DLQ. So this is how we can also design for the failed tolerance systems. Microservices and cloud infrastructure. As I said before, that we will use the Kubernetes cluster. So we will have the API gateways. As I said before, when the user request first comes in, right? So here you can see that this is the user request, right? Now, so this is the user. So this is a user request. Now the user request doesn't come into the Kafka. The Kafka is only for the data ingestion part. It doesn't come under when the user asks any query. So what happened when the user asks any query? So the first it goes to the API gateway. Okay. From the API gateway, it goes to the desired service, right? So it goes to the desired service. So you can say that these are the two part. So the first part is so this is not the first part. This where the data ingestion part is there, and this is the second part where the user asks any question, and it goes to the API gateway, and then it redirected to the desired services to get the result. Okay. So here the API gateway, it goes to the user service, the ingestion service, or the chat service, right? Then scalability and performance, how we can introduce the scalability and performance. So this is a completely stateless service as I discussed before. So we scale out. So instead of scaling up, the Redis caching we will use. So stores frequent queries in the RAM, avoids the recomputing expensive graph traversals. The Thunder Herd problem. So what is the Thunder Herd problem? Addressed by setting random expiry times on cache keys, so the database is not hit all at once when keys expires. This is very important, and this is part of the caching mechanism. Security, governance, and observability. So this is a multi-tenancy and the role level access. So company A cannot ever see company B's supply chain data. This is a strict authorization. How we can achieve that? We can achieve that by using the for every client or every tenant's unique ID. And for the observability, we taking a single user request journey across 10 different microservices to instantly spot bottlenecks. Then how we can introduce the background intelligence workflow. So for that, we can run the graph traversal algorithms. So there are multiple graph traversal algorithms. So algorithms continuously search for the shortest path of failures or single point bottlenecks. Then dynamic updates. So risk scores decay or increase are based on real-time news and historical trend analysis. So you can see that this is completely a loop that we will run some time interval which run the graph traversal algorithm, some search in the database, some machine learning algorithms will run. So this is how we can detect some anomaly early and notify to the user. So this is the end-to-end workflow of the whole system, of the whole application. So first the user upload the document, right? Then we run different pipelines. We have the monitoring systems. Then we analyze. So the analysis part is done in the background, right? And how we can do the analysis here, we have discussed that we have multiple services. So along with these four services, we have some other services, and that services run in time intervals. So one service may run some graph traversal algorithms which do the shortest path finding, or some graph data science. It uses some graph data science library to extract the information of the knowledge graph, find some anomaly over there, and inform early to the user. So this is the operation of the service. Then the ask, so the user can ask questions, and then finally the retrieve and the alert monitoring systems. So what we have discussed, so we have discussed the system foundation, we have discussed the dual brain strategy, so how we can implement the knowledge graph and the neo4, the vector database. We have discussed the AI guardrails, that why we should not just directly depend on the LLM to generate the response, why we should have created multiple steps, and that comes under the AI guardrails. We have also discussed the GraphRAG mastery. We have discussed the GraphRAG, the flow, right? The proactive intelligence, the enterprise ready systems. So all of these things we have discussed. Now, I know that this is a very high level of discussion. Okay, we can break these things further. And for that, if you really want to learn AI system design in more details, more in depth, then I have created one course in Udemy. You can, or you should definitely check out this course if you really want to go deep into the architecture of AI system design. Okay. And this is the course AI system design for engineers and interviews. Now, if you're really interested in system design or AI system design, how we can design production scale enterprise AI systems, then you should definitely check out this course, right? In this course, I go deep into the architectural discussion. I take multiple real world use cases, and I go deep into all these use cases. I explain that how we can design the AI systems, okay, how we can scale it, right? Everything I have discussed in this course. Now if you're interested, you should definitely check out my course on Udemy. So that's all from this video. I hope you understand the video, and I will see you in the next video. Thank you.